This is a question on RSA encryption, and as the question suggests, we have two parameters for RSA algorithm, n and e. N is equal to the product of two prime numbers, usually denoted p and q, and e is the exponent value, and the typical value, the typical property that e has to satisfy is that it should be relatively prime with these values p minus 1 and q minus 1. This is important in the decoding of the RSA encrypted data. Well, this is a simple question because this was in an in-class exam, and therefore the numbers are very simple. Obviously, in reality, we do not use such numbers, but for the purpose of demonstration, we are going to use these simple numbers. N is given as 39, and that suggests the prime numbers p and q must be 13 and 3. Doesn't matter which one is p, which one is q, because we are interested in their product as well as the product of p minus 1 and q minus 1. So in this case, that's equal to 12 times 2, 24. So it's no coincidence that we have a modulo 24 in the remainder of this question. Okay, and obviously the exponent value 11 is both co-prime with 13 minus 1, which is 12, and 3 minus 1, which is 2, because, well, exponent e itself is a prime number. Now, to encrypt this given data, we need to compute, well, this if each number here is taken as the message, what we need to compute is m to the power e modulo n. So to encrypt this given data, I need to compute four values. First of all, 8 to power 11 modulo 39, and also 12 to power 11 modulo 39, 4 to power 11 modulo 39, and finally I need 23 to power 11 modulo 39. Okay, so let's try to do this. And here you see Fermat's-Little theorem is not applicable because by its definition, n is not a prime number. Therefore, we are going to resort to the simpler technique. 8 to the power 1 is under modulo 39 is congruent to 8. 8 to the power 2 is 64. So that would be congruent to what under modulo 39? So if you subtract 39, you get 25. 8 to the power 4, that would be the square of 25 under modulo 39. So that's 625. So I need to find 625 modulo 39. Let me just put that to a computer, which would be much easier. Well, this was a final question. This is nothing that you cannot solve using pen and pencil, but let me just skip that in the interest of time. 625 modulo 39 gives you just 1 modulo 39. That's good news because that means 8 to the power 8 is also 1. And to obtain 8 to the power 11, I just need, 8 to 11. That would be congruent to 8 to the power 3 under modulo 39. So that would be 8 to the power 2, which is congruent to 25 times 8. So that's 200 modulo 39. And that makes 5. So I'll just give the value here as 0.5, let's say. Okay, the next one, I need 12 to the power 11. Again, to find that, I can just write 12 to power 1 is 12, 12 to power 2 is 144, which is congruent to 27 modulo 39. Well, to find 12 to the power 4, you can either square 27, or the easier way is recognize that 27 under modulo 39 would be equivalent to minus 12 modulo 39. So square of 27 would be congruent to square of minus 12, which is again 144, which is congruent to itself under modulo 39. So again, the same will be observed for 12 to power 8, which will give you minus 12. And therefore, to obtain 12 to power 11, I just need 12 to power 8 times 12 to power 3. And that can be written as 12 to power 2 times 12. And that would be 12 to 8, as we have just seen, is minus 12. 12 to power 2 is again minus 12. And we have another 12. Right, that would be, this is 12 to power 2. That's congruent to minus 12. And this would be just negative 12 times 12. And that, as we have observed, is, this is minus 12. Therefore, this is just congruent to 12 under modulo 39. So this is congruent to 12. Then I need 4 to the power 11. Again, 4 to power is 4. 4 to power 2 is 16. 4 to power 4 is 16 squared. That would be 256. And that under modulo 39 is congruent to 29. And you can either write this as 22, or you can write this as minus 17. I'm not exactly sure which one is easier to use. With pen and paper, I'll just continue. 4 to power 8 is the square of 22. That would be 4 times 121, so that's 484 modulo 39. And that would give you 16. Again, an observation here, 4 to power 8 is congruent to 16, similar to 4 to power 2. So we have a cycle here, and we just need 4 to 11. That would be 4 to 8 times 4 to 2 times 4, and 4 to 8 is congruent to 16. 4 to power 2 is also itself is 16, and we have another 16, and square of 16 we have computed as 4 to power 4, which is congruent to 22 times 4, you get 88, and 88 under modulo 39 is just 10. So this is 10. And finally, I need 23 to the power 11 under modulo 13. So let me just make some space here. 23 to power 11. So you can either use 23 here, or you can use minus 16 to power 11, because they are congruent. And that would be, well, you can write this as, well, I have, this will be an odd power, therefore the minus will remain. So I can just write this as minus 16 to power 11. And I can write 16 as 4 to power 2, and therefore this will give me 4 to power 22. And since I have the powers of 4 here, I can use them again, and 4 to power 22 can be written as 4 to power 16 times 4 to power 6, and 4 to power 6 can be written as 4 to power 4, 4 to power 2. Okay, so 4 to power 16 is the square of 16, because that would be the square of 4 to power 8. And we have already seen that square of 16 under modulo 39 is 22. So this would be 22. 4 to power 4 is also 22. And then I have another 16 here. Now here I have the square of 22, which we have shown to be, well, this was 22. We have taken its square to obtain 16. So this will be 16 again under modulo 39. And that gives me the square of 16. And square of 16, from here, I can see that that is either 22 or minus 17. And since I have a minus here, I can just write this as 17 modulo 39. So this part here is going to be just 17. Okay, so that's the answer to part A. And this is how you compute it. And obviously, usually you don't do this with pen and paper. You obviously use a computer to do that. And let's move on to part B. And again, I'm going to need some space, so I'm going to erase this part. So in part B, I need to find the multiplicative inverse of 11 under modulo 24. So question is formed in this way, but as you see, whatever x is, it's the multiplicative inverse of 11 under modulo 24. Now, since the numbers are small, you can either do this using trial and error, or you can also use the Euclidean, or rather extended Euclidean algorithm to find the Bezout coefficients. Let's do that quickly, because I know that 11 is a prime number. It will definitely be co-prime with 24. So I know that GCD of 24 and 11 is going to be equal to 1. But just let's apply the Euclidean algorithm here. 25 divided by 11 will give you a remainder of 2. So I will form this. I will write 24 equals 2 times 11 plus 2. And then you will divide, well, this will mean GCD of 24 and 11 is equal to GCD of 11 and the remainder 2. And then divide 11 by 2, you get a remainder of 1. So I can write 11 as 2 times 5 plus 1. That means this is equal to GCD of 2 and 1. And obviously, when you hit 1, the next step is obvious. You will divide 2 by 1, and the remainder will be 0. Therefore, this will be equal to GCD 1 and 0, which will be directly equal to 1. And the algorithm will stop. The only thing I need at this point is the Bezout coefficient. So I'm going to work my way backwards. So I can write this remainder 1 as 11 minus 2 times 5. And I can replace this 2 here, with this relationship here. So that will be 11 minus 5 times 12 minus 11 times 2. And that will give me 11 times. So I have 1 already here, and minus 5 times minus 2 gives me plus 10. So that is 11 times 11 minus 5 times 24. Okay, so these are the Bezout coefficients. Let me put that over here. 1 equals 11 times 11 plus minus 5 times 24. So 11 here and 24 are the numbers that I was computing the GCD for. 1 is the GCD, and therefore this and this is the Bezout pair. So the Bezout coefficients are 11 and minus 5. And obviously under modulo 24, I do not care about this one because that's congruent to 0. And that means under modulo 24, 11 times 11 is congruent to 1, meaning that x here should be equal to 11, which is also correct. Well, you can just simply verify this because 11 times 11 is 121, which is 1 more than 120, which is 5 times 24, obviously. And therefore, the multiplicative inverse of 11 under modulo 24 is itself. Okay, so why is this a question here? Because this is an RSA question. So why am I computing the multiplicative inverse of 11? And the reason is 11 is the exponent value, and the modulo value here, 24, is equal to this quantity here, p minus 1, q minus 1. And therefore, what we have computed here is what is referred to usually as D, the multiplicative inverse of E. And in this case, that's equal to itself under modulo 24, p minus 1, q minus 1. So that's going to be required when we attack part C, because in part C, we want decryption. If you recall, to decrypt a message using RSA, you need to know the D value, which we know to be 11 in this question. And what you need to compute is C to power D under modulo N. Now, as you see, the C values, the code word given to us in part C is exactly the same with the message value in part A. So in part A, we encoded this given message, and the result was 0, 5, 12, 10, and 17. And in part C, this is the code word now, it's not the message. So I just want to decrypt it. But to decrypt it, I need to compute C to the power D modulo N, and D is 11, N is 39. So the result will be exactly the same because D and E values are the same. And therefore, the answer to part C is exactly the same with the answer to part E, A, 0, 5, 12, 10, and 17.